In this video, we're going to take a look at question number 6 from the 2008 AP Chemistry Free Response questions. And in this one, we're specifically looking at molecular structures and intermolecular forces, which are commonly referred to as IMFs. So in A, it says structures of the pyridine molecule and the benzene molecule are shown below. Pyridine is soluble in water, whereas benzene is not soluble in water. Account for the difference in solubility. You must discuss both of the substances in your answer. So one thing that you should be somewhat familiar with is that hydrocarbons, like true hydrocarbons where it's C some number, H some number, those will always be nonpolar. Okay, so those aren't going to dissolve in water, and the reason is that hydrocarbons, a carbon-hydrogen bond is not polar, and there are no lone pairs. And we've talked in class about how you either need polar bonds or you need lone pairs that cause dipoles to not cancel to make a molecule polar. And if a molecule is polar, it's going to have a really high probability that it will be soluble in water. So what we have going on here is a lone pair on the nitrogen and pyridine. So what I would say is that we have got a couple reasons. The nitrogen in pyridine has a lone pair, which creates a dipole moment that is not canceled. This added polarity enhances, I guess we could say, pyridine's ability to dissolve in water. You could also make an argument that because that is a nitrogen, and we know hydrogen bonding occurs with fluorine, oxygen, and nitrogen, that the hydrogen in water can hydrogen bond with the nitrogen in pyridine, also enhancing pyridine's ability to dissolve in water. Now, one thing here is I think I have a really good answer, but I would not get full credit because they say you must discuss both of the substances. So I need to make some sort of mention about benzene. So what I'd add is benzene is nonpolar. And I might say no polar bonds or lone pairs, because those are one of those we need, or both, to make something polar. Lone pairs of electrons. And benzene cannot hydrogen bond with water. Thus, benzene is not soluble in polar water. Okay. Now, in B, it says structures of dimethyl ether and ethanol are shown below. The normal boiling point of dimethyl ether is 250 K. Oops. Whereas the normal boiling point of ethanol is 351 K. Account for the difference in boiling point. So hopefully this OH here is really sticking out to you. So one thing to know is, and I'd start off my response this way, is substances with stronger intermolecular forces will have higher boiling points every time. So because ethanol has the higher boiling point here, and ethanol must have stronger IMFs than dimethyl ether. Okay, now ethanol has LDFs, as does everything. Dipole because it's polar, and I know it's polar because it has hydrogen bonding. If it has hydrogen bonding, you can go ahead and say it has dipole. And then I would say dimethyl ether only has, and this isn't a great representation. I don't like when AP does this. These lone pairs make it seem like they'll cancel out, but they really won't, because this is going to be a bent oxygen molecule, so we really have our lone pairs like this, where they don't cancel. So I'd say dimethyl ether has LDFs and dipole. The stronger IMFs in ethanol, for example, specifically the hydrogen bonding, leads to ethanol having the higher boiling point. Okay, so in C it says SO2 melts at 201 Kelvin, whereas SiO2 melts at 1883 Kelvin. Account for the difference in melting points. You must discuss both molecules. So this one's a little bit difficult. Now remember, this comes from 2008, and we're going to talk about covalent network solids here, and those are not a big focus on the AP test since 2014, I believe. So we're going to talk about them, but understand that after 2014, covalent network solids are less of a focus on the AP test. So SO2 molecules, if we draw them out, are attracted to each other via LDFs and dipole. Okay, SO2 is definitely polar. Now, SiO2 is a covalent network solid, and thus is held together via covalent bonds. And covalent bonds, I can't spell today, goodness. Are not intermolecular forces, but they're intramolecular forces. And are much stronger than LDF or dipole-dipole intermolecular forces. These stronger forces, the stronger forces in SiO2 lead to a much higher melting point. Okay. Don't love that question just because it's less relevant since AP's updated their curriculum. So in D it says the normal boiling point of Cl2 liquid is 238 Kelvin and it's higher than the normal boiling point of HCl 188 Kelvin. So account for the difference based on the types of intermolecular forces in both substances, and we need to discuss both. So HCl has LDFs and dipole-dipole, and Cl2 has only dipole-dipole. So you would expect Cl2 to have the lower boiling point, but it doesn't. Cl2, they say, has 238, whereas HCl has 188. So based on what we've said earlier, substances with stronger IMFs will have higher boiling points. So Cl2 must have the stronger boiling point. And I've just noticed I said something wrong. Cl2 does not have dipole-dipole. I meant to say LDFs. So I apologize if you were confused there for a second. So why would Cl2 have stronger intermolecular forces? And a thing that you'll need to know is that more electrons leads to stronger LDFs. Okay, so I'm sure we're going to say that somewhere here in this answer. So substances with stronger IMFs will have higher boiling points. Cl2 must, or let me say it this way, the LDFs in Cl2 must be stronger than the LDFs in dipole-dipole in HCl. Cl2 has more electrons than HCl, so this makes sense because more electrons in a substance leads to stronger LDFs.